Hi, welcome to my channel. I am Aravindan. This is the 9th lesson in electric field. Mainly I focus Edexcel, Cambridge and International Baccalaureate syllabuses, but students, those who are following even AQA, OCR also can use this lesson or follow this lesson. Okay, in this lesson, I'm going to discuss about equipotential surface. What is it? What is equipotential surface? So equipotential surface means the surface that passes through points with same potential. Say consider a point charge kept in space. If a charge Q is kept in space, then it will create electric potential around it everywhere. At a distance r from the charge, the electric potential is given by V equal kq over r. Okay, so I can find infinite points around the charge q in 3 dimensions. Is it? At say for example, if it is 5 centimeter distance, then I can find infinite points from this is the point charge. So I can find 5 centimeter, 5 centimeter, 5 centimeter, 5 centimeter, 5 centimeter, like that. I can find infinite points around the point charge Q at the same distance. So that means on all those points, the electric potential will be the same. So if I connect all those points, I will get a sphere, is it? Spherical shape will be formed. I'll get a sphere. On that sphere, the surface of the sphere, the potential will be the same. That sphere is an equipotential surface. So how many equipotential surfaces can I have around a point charge? Actually, we can have infinite different equipotential surfaces. Say for example, if this is the charge Q, I can find an equipotential surface. It's a sphere at a distance r1 from it, at a distance r1 from it. Then another equipotential surface around the charge Q, I can find at a distance r2. Like that, I can find infinite equipotential surfaces around a point charge. Okay. Now consider 2 points on an equipotential surface. Say for example, this is a point charge Q. It creates an equipotential surface at a distance r from it. Okay, on that sphere, consider 2 points x and y. Both x and y will have the same potential. Both will have the same potential, V equal kq over r. So the potential difference between these 2 points, delta V, will be equal to kq over r minus kq over r, that will be equal to 0. So when we consider any 2 points on an equipotential surface, the potential difference between those 2 points will be equal to 0. So when you consider potential difference 0, so we'll get immediately an idea about work done. Okay, if I move a charge Q, if charge Q moves from x to y, then the work done on the charge, when it moves in electric field, the work done is given by the previous videos. We learned that W equal Q times delta V. That is Q times delta V means Vy minus Vx. But Vy, Vx both have the same magnitude. So the work done will be equal to 0 because potential difference between x and y is equal to 0 regardless of the path it takes. The charge Q might take a path along the surface, or it might take a path something like this, or it might take a path something like this way. Whatever the path it takes from x to y, the work done will be equal to 0. So that means when the charge particle symbol Q moves from x to y, it won't gain any energy. At the same time, it won't lose any energy. The energy possessed by it will remain constant. So that means now you might get an idea. Okay, the charge Q, when it moves from x to y, is experiencing electrostatic force, is it? Because it's moving in the electric field created by the charge capital Q. So if I consider the motion from x to y along the equipotential surface, because I am going to analyze what can be the angle between the electric field and the equipotential surface. So that is the purpose. So I consider a special case in which the charged particle symbol Q is moving from x to y along the equipotential surface. Okay, when it moves along the equipotential surface from x to y, if it experiences any force along its direction of motion or opposite to the direction of motion, according to W equal force into distance moved dx, maybe a small distance it moved on the way dx. So if it experiences any electrostatic force along the direction of motion or opposite to the direction of motion, when it moves along the equipotential surface, careful, I am specially considering along the equipotential surface, the motion part. So then there will be work done. If it experiences any electrostatic force along the motion, is moving along the equipotential surface. So that means when it moves from x to y, we know that the work done is already 0. We got it since equipotential surface. So when it is moving from x to y, the work done is equal to 0. That means F must be equal to 0. So what do you mean by F equal to 0? When the charge Q moves along the path from x to y along the equipotential surface, it should not experience any electrostatic force along the direction of its motion. You know, electrostatic force is given by F equal QE. So if this charged particle has no electrostatic force along the direction of motion, if this force is equal to 0, that means Q must be equal to 0 along the equipotential surface. But there is electric field which is emitted, created or given out by the charge Q. So that electric field created by charge Q should not have any component along the equipotential surface. That's the final conclusion I can say. The electric field created by charge Q should not have any component along the direction or along the surface, equipotential surface. That means the electric field should be in right angle to the equipotential surface. Are you clear? So electric field lines should be always in perpendicular to the equipotential surface. They should not have any component along the equipotential surface. That's a very important conclusion based on equipotential surface. Okay, again, remember that always the electric field lines should be in right angle to the equipotential surface, right? I explained based on work done, right? But it can be explained based on the equation E equal minus dV over dx. That means electric field strength at a point is the potential gradient is equal to potential gradient. Okay, if I consider this way, by using this also I can explain the electric field strength must be equal to 0. But in most of the A level, we don't use this format, the calculus format. But I can explain by using this also. Say for example, this is the charge. It creates an electric equipotential surface around it. Okay, consider a small portion of this equipotential surface, delta x. In this delta x, okay, on that delta x, the equipotential surface, the dV, that is the difference in potential, must be equal to 0. So that means dV equal to 0 means in that small region, the electric field strength along that dx, I consider the dx, in that small dx, dV equal to 0. If it wants to be 0, that means E must be equal to 0 along that surface. That is, the potential gradient must be equal to 0. If the potential gradient on that surface equal to 0 means the electric field should not have any component along the surface dx. That means obviously the electric field line must be perpendicular to the equipotential surface. Okay, by using this very important conclusion, we can draw equipotential surfaces for different electric field line patterns. In my second video, I drew the electric field lines for point charges. When 2 point charges are kept, the overall electric field line patterns, I drew it. So for that type of electric field line patterns, I can draw the equipotential surfaces by considering the equipotential surface must be perpendicular to the electric field line. By using this concept, we can draw the equipotential surface anywhere if we know the field pattern. Okay, so we'll draw some equipotential surfaces in different field patterns. Okay, so here you can see that in all these diagrams, the red color lines indicate the equipotential surface and the blue color line indicate the electric field. So you can see in all these diagrams, electric field lines are perpendicular to the equipotential surface. Blue color lines are in right angle to the red color lines. See, everywhere, you know, there's a radial field. So the radius is perpendicular to the surface of a sphere. So here also, first, if you want to draw the equipotential surface, you should know the field pattern. So draw the field patterns, which is given by blue color. Then you draw the equipotential surface such as the surface at every point is perpendicular to the electric field lines. At any point, if you consider where the blue color line and red color line intersect, at any point they will be in right angle to each other. They are perpendicular to each other. Same way here also, when two positive charges kept in space, they create field pattern as shown here. So equipotential surface everywhere at every point, the equipotential surface, that red color line is in right angle to the blue color line. Okay, this is parallel plates. The equipotential surfaces are parallel to the plates. Field lines are perpendicular to the plates. At any point, blue color line and red color line are perpendicular to each other. And here also you can say this is a conductor. So conductor is an equipotential surface. You know that because conductor at all points the potential is the same. We learned that earlier. So it's an equipotential surface. So if you keep a charge, a point charge, for example, I took a positive charge, then the field line should fall or touch the surface of the conductor in perpendicular to the surface of the conductor. So the surface of the conductor itself is an equipotential surface. Okay, we'll discuss this question. So it's a uniform electric field. You know, the field lines are parallel to each other and the field is directed towards left, and the electric field strength in this uniform electric field is 1500 Newton per Coulomb. An electron is entering, now the electric field is starting at this line, right? So an electron is entered into the electric field at point X at a speed of 2 into 10 to the power 4 meter per second. Okay, when it enters, after it enters into the field, you know, it's going to experience electrostatic force towards opposite to the direction of field line because electron is a negatively charged particle. So I earlier explained that always a negative charge will experience electrostatic force opposite to the field line. So the electron is entering along this way. Then due to the force towards right, it's turning and reaching the point Y finally. So the distance between X, Y is 10 centimeter. Those all are given in the question. And the line XY is making an angle 30 degree with the field line. Okay, so mass of the electron is given. Charge of the electron also given. The first part, find the potential difference between the points X and Y. Okay, so between the points X and Y, they are asking to find the potential difference. Okay, the method here, it's like this. You know the in uniform electric field, the equipotential surfaces are always right angle to the field line. So if I draw a line, vertical line, I'm answering now, vertical line, along this line, the electric potential will be the same, will be equal. So if I want to find the potential difference between x and y, instead of finding it, if I find a potential difference between a point on this surface, which is along this line, if I find the potential difference between point z and y, that will be same as the potential difference between x and y. Okay, so I draw a vertical line, that's an equipotential surface. Then I drew a line from y to this line such that it is right angle to the equipotential surface. So instead of finding the potential difference between x and y, I can find the potential difference between z and y. And we know that in uniform electric field, we learned that the electric field strength and the potential difference are given by E equal V over D. There is a minus sign. We don't use the minus sign. What's the condition to use this equation? On an when you consider the uniform electric field, so what's the condition to use this equation? In a uniform electric field, if I know 2 points along the direction of field, x and y, and if I know the potential difference between those 2 points is V and the distance between those 2 points is D, then the electric field strength is given by E equal V over D, where V is the potential difference in terms of magnitude. So I should know 2 points along the direction of field and now parallel to the field lines. 2 points I should know. I should know the distance between the 2 points and the potential difference between the 2 points. So that's the reason on the parallel to the field line. So you know xy is not parallel to the field line. So I want to find the potential difference between y and z because y and z are on the line that is parallel to the field line. And only thing I need to find the length of zy or the distance between z and y. If I find it, I can use E equal V over D since I know the electric field strength. So this is 30 degree with field line. So with this vertical line, that will be 90 minus 30, that is going to be 60 degree. That is going to be 60 degree with the vertical line. Okay, so if that is 60 degree, I can find the length zy since I know the line xy, that is 10 centimeter. So I can say zy equal to 10 sine 60. If you solve it, you will get the length of zy. Okay, so we know the length zy, that is 0.087 meter, right? So now we can find the potential difference between z and y. So because that line is parallel to the electric field line, so I can say E equal V between z and y over distance, that is distance zy. So electric field strength, I know that 1500. The potential difference between z and y, I am going to find the distance zy. You know that 0.087 meters. So potential difference of zy will be equal to, you will get an answer of 130.5 volt. That is, I found the potential difference between z and y. But z and x are same potential, equipotential surface because the line is perpendicular to the field line. So potential between x and y is also the same. So potential difference between x and y, that's a question, no? Find the potential difference between x and y. So Vxy also 130.5 volt. Okay, second part. Find the electrical work done on the electron when it moves from x to y. Okay, so what's the electrical work done? We know the electrical work done in electric field is given by W equal Q times delta V. Delta V is the potential difference. So I told that the work done does not depend on the path. It depends only on the initial and the final point. Whatever the path it takes, it does not it won't decide the work done. Work done depends only on the initial and the final points. So we know the potential difference between x and y. So I can write that is q into Vxy. So charge of the electron is given 1.6 10 to the power minus 19 into Vxy. We found it in the previous part. We found the potential difference in the previous part, that is 130.5 volt. Solve it, you will get the answer for the work done. That will be 2.07 into 10 to the power minus 17 joules. 2.09. 2.09 into 10 to the power minus 17 joules. Okay, so third part, find the speed of the electron at point Y. So in the question they have given the initial speed, the speed at which it enters into the electric field is 2 into 10 to the power 4 meter per second. So the initial speed is 2 into 10 to the power 4 meter per second. So the question is find the speed at point Y when it moves through the electric field. Okay, so when the electron moves through the electric field, when it moves this way, is it going to accelerate or decelerate, or is it going to gain kinetic energy or lose kinetic energy? Actually, it's going to gain kinetic energy because it's entering in this direction. So when the electron is somewhere inside, imagine that the electron is somewhere inside, it's going to experience electrostatic force this direction. So there will be a component of force that is going to accelerate the electron. So it's going to gain kinetic energy when it reaches the point Y. So we can find the gain in kinetic energy. We can find like this: gain in kinetic energy equal work done by the electric field. So that is half mv squared minus half mu squared. That is equal to the work done. We found it in the previous part. Okay, so we know half times 9.11 10 to the power minus 31, same mass, I'll take it common, v squared minus initial speed is 2 into 10 to the power 4 all the square is equal to the work done. We found it in the previous part, that is 2.09 into 10 to the power minus 17 joules. Solve it, you will get the final speed v, that will be larger than the initial speed. You will get the final speed, that will be 6.77 10 to the power 6 meter per second. So when it moves in the electric field, what can be the path of the electron? So electron would have taken a path something like this. So it's not going to move on a straight line from x to y. Certainly it will not move on a straight line. So it would have followed a path, a curved path, something like this, curved path, maybe something like this. It's entering this way. So initially the line is this way. It would have moved something like this. Okay, it would have gone something like this. Okay, that will be the path. So it's gaining kinetic energy. So the final speed is more than the initial speed. Okay. So this is a good example how to use the idea of equipotential surface in certain questions. Because I can't use E equal V over D directly for X and Y because X and Y are not lines parallel to the electric field. Okay, so I explained that when I was teaching about E equal V over D, how to use that equation. Okay, that's the reason I found the length X, Z, ZY. Okay, I hope you understood all these things. So Theory wise, that's all for Edexcel, Cambridge, AQA, OCR, all the syllabuses. So based on electric field, Edexcel continues with after this capacitors, even Cambridge continues capacitor. IB, it's a separate topic. So I'll discuss capacitors in a separate video. So next video, I'm going to discuss past paper questions, Edexcel past paper questions based on electric field. Then separate video for Cambridge past papers. Then International Baccalaureate high level past papers. Then after that, I'll discuss AQA and OCR past papers together. Okay, so that's the way I'm going to continue these videos. Right, we'll meet in the next video. Bye.